Okay, this is a genetic algorithm that a video that my brother-in-law sent me a couple weeks ago, sort of inspired, except that video, beautiful, beautiful work, was demonstrating evolution through a genetic algorithm that also incorporated neural networks. Well, my algorithm has no neural networks because I have no idea how to code them. So let me just get it started. And I built this, I built 10-second delays into it that I can generate by clicking. So I'm going to just click for a 10-second delay and explain something. First of all, there are 36 chromosomes, or you might think of those as individuals, each of which has 12 genes. And each gene is randomly chosen through four different directions: north, east, west, or south. So that's what the N, S, W, and E stand for. So we have 36 organisms produced randomly and with their genes produced randomly. And the situation is, how do we determine fitness so that we can find the parents for the next generation? Well, fitness is how many E's there are in the chromosome. So when you start off, there'll just be a random, chances are 1 out of 4 that there will be an E in that 12 gene chromosome. All right. For each of the genes, the chances are 1 out of 4. So anyway, we then do some sorting and we find the 2 chromosomes out of the 36 that have the most E's. Those become the parents of the next generation. All right. And I did not know quite how many crossovers to make, so I did 30 crossovers, and each of those crossovers produced another chromosome. So out of the 36 total, 30 of them are produced through crossovers, and then the remaining 6 chromosomes of the next generation have their 12 genes selected randomly. So that's really a high mutation rate right there, which is probably one reason why it works so well, because of the randomization. I don't know. Anyway, it usually takes under 20 generations for all of the offspring to make it to the east side. In other words, to get more and more and more E's in their chromosomes, which you can see here, all these E's mounting up. So I'm going to start it over, shut up, and let you watch it work. Okay, now you notice that there are a whole lot of E's in the chromosomes here, and that's because the parents had a lot of E's in their genetic makeup to pass on to each new generation. And the more E's they had, the more likely they were to become parents and produce offspring with lots of E's. And I guess you figured out that an E means it moves one step to the right, okay? All right, so let me stop it again and explain something. How can I say it? Each step, okay, each chromosome takes 12 steps, right? And the steps are this sequence. So let me stop it. So, for example, the first step would be north, the next would be west, the next would be east, the next would be east, the next would be west, the next would be west, another west, then an east. Okay, so the more east there are, the more tendency there will be for it to move to the right. So we want as many E's as we can get, so we select the 2 parents with the most E's, and those are the ones that breed the next generation. It doesn't always work. Sometimes there are anomalies. Sometimes it goes backwards. And this time it's struggling, okay? We've had 11 generations already. Sometimes it gets across in like 6 or 7 generations. Here we are with 14 or 15, and it's just dithering out. So let's get it started again and so we can do better. This time it's working pretty well. Okay, one more and that's it. What you notice here is that each new generation has more E's in the chromosomes. And that'll do it. Thank you for watching.